All right, let's get right into it. Today, we're going to peel back the layers of the Linux kernel and take a look at something that's absolutely critical for networking and security: packet filtering. We're going to trace the journey from the classic tools that honestly built the early internet, all the way to the modern stuff that's making everything faster and way more efficient. So let's start with the big question, right? When you type in a firewall rule, what is actually happening down in the guts of the operating system? How does your Linux box decide, okay, this packet gets in, this one gets dropped, and this one, we'll send it over there? Believe me, it's not magic. It's a really cool, highly structured system that's seen some serious evolution over the years. And right at the heart of it all is a thing called Netfilter. Now, this isn't some program you run from your command line. You can't just type Netfilter. Think of it more like the fundamental architecture, the bouncer, the gatekeeper, that's built directly into the Linux kernel itself. It's what makes everything else possible. Now, check out the keyword on this slide: framework. Netfilter doesn't actually make any decisions on its own. What it does is provide a series of hooks. Think of them like checkpoints or little attachment points inside the kernel's networking code. Other programs can then come along and latch onto these hooks to look at, maybe change, or just flat out drop packets as they fly by. It is the foundation. Everything else is built on top of this. So let's follow a packet on its little adventure, okay? Think of it like a highway with mandatory exits and checkpoints. Any packet coming in from the outside, bam, it hits the pre-routing hook first. From there, the kernel asks a simple question: is this for me? If yes, it goes to the input hook. If it's just passing through to another network, it goes to the forward hook. Now, what about packets created on this machine? They start their journey at the output hook. And finally, everything, coming or going, makes one last stop at post-routing, right before it jumps onto the wire. Each one of those hooks is a place where we can apply a rule. Okay, so if Netfilter is the framework, how do we, as humans, actually talk to it? Well, for decades, the answer was iptables. This was the command, the user space tool, that was the absolute king of Linux firewalls, the long-reigning champ of packet filtering. And this is what that conversation looked like. Yeah, this command is a perfect example. It's basically telling the kernel, hey, go to the output chain, use this cgroup module to find any packet that is not from this specific control group, and then jump to the drop target, which is a fancy way of saying throw it in the garbage. This cryptic syntax was the language that admins had to learn to speak. But, iptables started to show its age. It got a little creaky. If you wanted to filter IPv6 traffic, you couldn't use iptables. You had to use a totally separate tool, IP6 tables. ARP traffic? Yep, another tool, ARP tables. It was fragmented. And even worse, you had to use these complex, kind of hacky workarounds for modern networking. The BR Netfilter module is the classic example of this. It exists for one reason: to trick iptables into filtering bridged traffic by making it pretend it was routed traffic. That's a huge red flag that the design was being stretched to its limits. And you don't have to take my word for it. Eventually, the kernel's own documentation just laid it all out there. This quote is basically the official turning point. The old way was stamped legacy, its use discouraged, and it pointed everyone directly to the successor, nftables. The writing was on the wall. The system had to evolve. And that brings us to nftables. This is the modern successor designed from scratch to be a unified, consistent, and, importantly, a high-performance replacement for that whole collection of iptables tools. And the advantages are just huge. With nftables, you have one single command, nft, that handles the whole shebang: IPv4, IPv6, ARP, you name it. The syntax is way cleaner, it's built for better performance, and this is a big one: it supports atomic updates. That means when you load a new set of rules, they all apply at the exact same time. No more weird race conditions or being stuck in a half-updated state. Plus, it just gets things like bridge traffic right out of the box. No more workarounds. You can really see the difference when you put them side by side. Look at this. It's the same transparent proxy rule written in both systems. The iptables version is just a sea of flags and switches. The nftables version, it reads almost like a sentence describing what you want to do. That simplicity isn't just for looks. It reflects a much smarter, more intuitive design under the hood. But the story doesn't stop there. This new Netfilter architecture unlocks some seriously powerful features that go way beyond just filtering packets. One of the coolest is something called the Flowtable, which is basically a super high-speed bypass for your network traffic. So, what is a Flowtable? Well, think of it like this. Once a connection is established, say a big file download, and your firewall rules say, yep, this is allowed, the flow table kicks in. It's like a high-speed cache. Instead of every single packet from that download having to go through all the Netfilter hooks over and over again, they get to take a shortcut. They completely bypass most of the network stack and go almost straight to the hardware. The performance boost is just massive. And here's the best part. Turning on this performance-enhancing feature is ridiculously easy with nftables. This one simple line is all it takes. You're just telling Netfilter, hey, for any TCP traffic that's already been approved, go ahead and offload it to this flow table I've created. It's a beautiful, seamless link between the modern firewall tool and a next-gen performance feature.
So this all leads us to a really fascinating, thought-provoking question. We've gone from a system of complex checkpoints that inspect every single packet to a system that's smart enough to know when to just get out of the way for the sake of speed. So if the future of high-speed networking is all about avoiding the very stack we've spent decades perfecting, what on earth does that mean for the next evolution of the Linux kernel? Something to think about. Thanks for tuning in.